Welcome back to our final section of Lecture 1. So we have Lecture 1H, and we're going to talk about things called London dispersion forces. So in the last lecture, I left you with a bit of a mystery, which is how do nonpolar molecules stick together, especially at really low temperatures? And it's due to these things called London dispersion forces. So the London dispersion forces are weak forces that are present in every single molecule or every single atom. If you have an atomic gas, it's still there. So it's not a molecular property, it's a property of atoms. And if you have a molecule, that those properties of those atoms extend to the entire molecule as well. So what are they? Well, they're individual interactions between molecules. It is an intermolecular force. Individual interactions are very, very weak, but if you have a large molecule, you can have, there's power in numbers, let me say that. If you have several atoms, then the individual interactions begin to build up, and in a large molecule can become very significant. It's a little bit like getting bit by an ant. If you get bit by an ant, it's not that big a deal. If you stand on an anthill and you have millions of them on you, you start to become a little concerned. Same kind of idea here. Now, sometimes you'll hear London dispersion forces, also called van der Waals forces, and they are technically different. London dispersion forces are a type of van der Waals force. There are other molecular forces that fall under van der Waals forces, and so we're going to try to stick with the more specific term, London dispersion forces. So let's just make this simple. We're going to imagine a molecule as just kind of a sphere of electrons, or having a sphere of electrons. So maybe something, like a methane molecule. It's tetrahedral. There's molecules everywhere. You can kind of imagine where those electrons within the bonds moving in their orbitals have kind of a spherical range of influence. So within that sphere, those electrons are distributed randomly. They're moving constantly, very quickly, roughly a tenth of the speed of light. So there is just a complete random distribution within there. Now, for whatever reason, just in randomness, for an instant, in that randomness, some or most of those electrons can be on one side of the sphere or one half of the sphere, depending on how you want to put your plane. Since the sphere has an infinite number of planes that runs through the center, it's very easy to have more electrons on one half than in the other half. What happens when that occurs? Well, for that instant, the molecule develops a teeny tiny plus, delta delta plus, and a teeny tiny minus, delta delta minus. Okay, and it's due to just, if we think of our half molecule right there, you can see that there's a lot more electrons in this region than in this region. And so the portion of the molecule that has more electrons is going to develop a delta delta minus, and the one that is lacking its fair share of electrons is going to have a delta delta plus. Now, again, the electrons haven't stopped moving. It was just for a moment. And so in the next moment, that tiny difference goes away, but it can reform somewhere else. So here we see another reasonable distribution of electrons. However, that random distribution where most of them are on one side and not on the other can form very easily. And so we see that we get another delta delta minus and a different delta delta plus. Notice that the directionality of the minus and plus are different for those two different instances. And so this is what we call a temporary dipole. It's a dipole that exists for just a moment, but then it's gone, but then it reforms in a different direction. And so the vector of the dipole is constantly changing. So it does create a dipole, but it's not permanent, and it goes away and then reforms in a different direction. Now, when a dipole forms just on a single molecule within a sample, we want to ask ourselves, how does that affect adjacent molecules? Well, we know that positives and positives repel, negatives and negatives repel, positives and negatives attract. right? Okay, so here we have our central molecule. So this is the molecule that developed the temporary dipole. So on this side, it's got a delta-delta minus. Now, this molecule probably had just a regular distribution, but those electrons in that electron cloud feel that negative charge from the temporary dipole, and that repels those electrons to go to another side. Vice versa, over here, we have that delta-delta plus, the teeny tiny plus over here. Well, pluses attract negatives. And so the electrons in this adjacent molecule are attracted to that teeny tiny plus. And what that does is it causes those molecules on the left and the right there to develop their own dipole. Because now this molecule, having had its electrons pushed to one side, developed a teeny tiny plus, or I'm sorry, a teeny tiny minus and a teeny tiny plus. The teeny tiny plus and the teeny tiny minus attract each other. Just like over here, the teeny tiny plus created this teeny tiny minus, and now they attract each other. So we call this an induced dipole. So the molecule in the middle had a temporary dipole, and then the molecules that are adjacent to it are going to create induced dipoles. Now you can imagine now that those molecules on the sides that have induced dipoles, well, they're going to induce the next molecule and then the next molecule and the next molecule, and et cetera, so forth. And that can go all the way through the sample. So you have these little tiny dipoles forming for just a moment, but then they're going away. Now, that can continue to happen throughout the sample through all of time. So as I said earlier, those London forces occur in all molecules, but their relative strength varies by molecule. So why do they vary by molecule? Well, it turns out that what determines the strength of those London forces is the number of total electrons in that molecule, because that determines the size of that shift from one side of the molecule to the other. So that changes the size of the delta minus and the delta-delta plus. Now, you will see some graphs occasionally that use molar mass as the determiner for the strength of London forces. It does follow the same trend as the number of electrons, so I understand why people use it, but I prefer to use number of electrons because that is truly what is creating the London forces, not molar mass. So the more electrons you have, the stronger the London force is. Now, when you have a small polar molecule, something like water or ammonia, or maybe something like methanol, the London forces are generally not very significant compared to the strength of the dipole. And so they do contribute somewhat to the strength of the attraction, but not very significantly. However, once you start getting into some large molecules, the impact of the London forces can become quite significant. Okay, so here we see a series of alkanes, pentane, hexane, heptane, octane, nonane. We know that these alkanes are all nonpolar molecules. Let's take a look at these boiling points. And so here we see pentane boiling point somewhere around like 38, so significantly below water. As we add another CH2 unit on there, it goes up to about 65, still well below water. We get to heptane, however, it looks like its boiling point is about 98, 99 Celsius, and so that's right on par with water. Now, this is a much larger molecule than water, but that's why its London forces, it has significantly more electrons than water does. And so it creates fairly sizable London dispersion forces. And then we start moving into octane and nonane, and we see that their boiling points are significantly higher than water. Nonane is up here at around 150, so much higher than water. So like we said right at the very start, individual London forces from an individual electron moving from one side to another is really very small. However, there is power in numbers, and you start getting to molecules of this size, and their London forces become quite significant. Okay, well, that finishes out all of Lecture 1, so hopefully you stuck with it and have watched all of these. Keep an eye out for a new set of lecture slides for Lecture 2.